Okay, so a quick little review. Last time we were talking about CPU, kind of this thing that does a whole bunch of magic tricks for us. We talked about three different kinds of programming languages: machine language, low level, high level. Low level having a one-to-one relationship with that CPU, so every line of code we write in this is equal to one line of one instruction, one magic trick on the CPU. We like these high-level languages that allow us to write one or two lines of code and it turns into a whole bunch of stuff on the CPU. Then I said there's two different types of languages. We have interpreted languages and compiled languages. We want to think about interpreted languages as being relatively slow. I think the example we used was the president giving a speech and we have the sign language interpreter or something like that. That's 2 or 3 words behind. So people who are experiencing the speech through that interpreter aren't getting it at full speed. Okay, so that would be kind of an interpreted language. Compiled language would be more like the same thing, but maybe the speech is going to be given in German and they send it to the translator a couple hours before the speech who translates it all ahead of time. And then the person who's actually delivering the speech in German is doing it in real time without slowing the process down. That would be more like the compiled language. Remind me, what's the purpose of a compiler? That would have been a good quiz question, I guess. Go ahead.
It translates the high-level code into low-level.
Okay, so compiler translates high-level kinds of programming languages we like to write stuff into low-level, a level that has a one-to-one relationship with the CPU. Okay, last thing we looked at last time was some different types of languages. Functional, I think we probably used the TI graphing calculator as our example. Procedural, that was the pile of wires that represents our cell phone over there. And object-oriented, where we think about a phone like this, where we know that the wires and stuff are inside, but we think about this object in terms of the public interfaces, the buttons and stuff that we use to actually utilize the object. If we really needed to get to the details, we could, but object-oriented languages give us tools for hiding those details once they're working. Okay? Let's see. There are two types of programming languages: domain-specific and general purpose. Okay, these are the types of problems that the programming language is designed to solve. So domain-specific languages are designed to solve a very specific type of problem. General purpose languages are designed to solve a large classification of problems, or a general set of problems. Okay, so the idea would be a domain-specific language would probably be much smaller than a general purpose language. General purpose languages have to have a lot of built-in stuff to allow you to solve a whole bunch of different kinds of problems. Chances are we've heard of several different high-level languages. What are the programming languages you've heard of before? Some of you may not have heard of them, but there's probably some buzzwords out there you've heard of. So what do you think you've heard of that might be a programming language? You heard of Java? Okay, that's a programming language. We heard of C++ before? Okay, those of you who took 150, I'm sure they talked about it in there, right? We heard of C#. Okay, another programming language. You heard of Objective-C? Maybe not that one. Okay, we'll talk about that in a lot more detail today. Okay, these are some examples of general purpose languages. Okay? Pretty much when we think of programming languages as computer scientists, we're thinking about general purpose languages. Okay? The Home Depot power tool that lets us solve a whole bunch of different kinds of problems. Now, there's some smaller tools that allow us to solve more specific problems. Now, and again, I'm going to warn you, I'm going to trick you. I'm about to trick you. All right, so how many of you have heard of HTML? Okay, what's HTML? Making web pages, right? It's the web page language. Would we call that a very specific job? Okay, so in your web browser, it interprets HTML to make text and pretty pictures show up on the screen, right? Okay, so that's a very specific thing. You're not going to create a missile launching software with HTML. Make sense? Making pretty web pages. That's the point of that. So my question is, remember, I'm going to trick you. Is HTML an example of a domain-specific language? Why? Huh?
Because you're tricking us.
Maybe I'm tricking you because I wanted you to say no, but the answer is actually yes. What do you think? We just said that it solves a very specific problem, right? Question is HTML a programming language by the definition we've put forth? What does HTML stand for? Anybody know? Hypertext markup language. So it has the word language in it, but does that mean it's a programming language? Now, the first thing I'll say is you could make an argument that it is a programming language, but it's not compatible with my definition of a programming language based on what I've put forth in here. So if we're just trying to stay consistent. Why not? Why isn't HTML a programming language? Let me jump back to the slide that has the, okay. The answer can be found on this slide. Why isn't HTML a programming language? Go ahead.
It's not used to really solve problems, used more to get information out.
But it does solve the problem of making things look pretty. But it is a text formatting language. That's a true description of HTML. It's text. It's a formatting language. Does HTML meet the requirement of mimicking the way human beings solve problems? How did we define the way human beings solve problems in here? These guys, right? We decided human beings, we use our memory, we ask questions, we use repetition. In a language like HTML, we have no way of remembering stuff. We have no way of asking questions. We can't repeat stuff. The language doesn't have those constructs built into it. So by our definition, this guy would not be a programming language. It's a perfectly usable tool, okay? And it's a perfectly good language, but it wouldn't be a programming language by our definition. You probably did a little HTML in 150, right? Made some little web page or something like that, or you just talked about it? Huh? Talked about it? Okay. How many of you in here who have ever made a web page using HTML or something like that? Now, so I've just advertised that it's missing those couple of features, those 3 features that really make it a programming language. Is there something that is often used in conjunction with HTML to provide those additional features? Kind of gives us a reason for the insanity for those of you who have done any web programming. Script. JavaScript. So there's a tool, a programming language called JavaScript, which is embedded inside of HTML. And the web browser knows how to execute this. The web browser interprets JavaScript at runtime. So that's an interpreter. It allows us to solve more general problems. JavaScript allows us to define variables for memory. It allows us to ask questions. It allows us to repeat things. So JavaScript allows us to augment our web pages to be a little bit more dynamic. Okay. Now, Couple points of interest here, more trivia things. JavaScript has nothing to do with Java. They just happen to share a portion of the name with each other. It's not based on Java. But in a few minutes here, we're going to actually talk about that many of these languages came from the same lineage. Okay, we see languages evolve over time. And JavaScript is based on an older language called C, just as Java is. So it does actually look similar to Java, but they're not actually related in any real way. The other thing is, since JavaScript, as its own individual language, has a bunch of constructs in it for solving general problems, it's probably fair to say that JavaScript is actually a general purpose language. It's commonly used for adding some dynamic capabilities to web pages. But anymore, it's also generally used, it's become popular to be used with game engines like we're going to use in here to add some additional functionality that's not built into it. GameSalad doesn't actually support JavaScript, but some more complex game engines that allow us to make video games in a drag and drop type feature allow us to pull off some more powerful things using a scripting language like JavaScript. So it's kind of a hybrid tool where it's some drag and drop and some programming. So realistically, this probably would not be the best example of a domain-specific programming language. We can certainly see HTML as a domain-specific language. A better example here for a programming language might be kind of what we talked about last time, the Texas Instruments language for the graphing calculators. It's a language specifically designed for solving math problems. Okay? The calculator lets you store things in memory. It allows you to ask questions and conditionally do things, and it allows you to repeat stuff. But you're not writing a video game. Well, actually, that's not true. Actually, it's any of you ever program your Texas Instruments graphing calculators? Ever write anything interesting on it?
I made a really crappy version of some.
Okay. I'm a little bit embarrassed to advertise this, but those calculators have been out forever, right? So when I was in high school, I had a TI-80 graphing calculator, and so I started programming when I was 9. So it's just always been, I'm like the weird geek guy, so I've been doing this for a while. And so when I was in high school, me and a couple of my buddies decided we were going to write a game for it. We named the game Ghettos and Gangsters. And it was a game about selling drugs. And it was a pretty complex game with it probably had about 17 hours of playtime on this graphing calculator. It was pretty bad. That's what we did during like breaks and study hall and stuff like that. We wrote Ghettos and Gangsters. There's something wrong with us. Still something wrong with me. All right, so in any case, that would be an example of a domain-specific versus a general-purpose language. All right, what we're trying to do here with several of these slides is really kind of look at programming languages through a couple of different lenses, through several different lenses, to give us an idea of what they are in the big picture. Okay? So, generally speaking, most of the languages we'll ever deal with will be general-purpose languages. Okay? Most of the programming languages we deal with will be general-purpose languages. Let's see. I just want to make sure I'm covering all of our slides here. So this is a high-level, compiled, object-oriented, general-purpose. There are two types of programming languages. We have loosely typed, and we have strongly typed. And I'm only going to be able to talk about this slide briefly, because then we actually have to insert our history of languages into this. So I'll give a little definition, but we'll have to finish explaining it after we talk about the slide that I need to put before this one. So a loosely typed language is a language that does not require us to define what kind of value a memory address will hold. So loosely typed languages do not require us, when we're creating memory to remember something, they do not require us to inform them what we intend to put there. Strongly typed languages does require us to define what kind of value a memory address will hold. And to kind of connect this to our other slides, we want to think about this guy as being associated with relatively slow languages. This guy being associated with relatively fast languages. We can also go on and say this guy is also associated typically with interpreted languages, which we advertise as relatively slow. This guy is typically associated with compiled languages, which we also advertise as being relatively fast. Okay? Part of that means that if we define a memory location and we don't say what kind of value we're storing there, when we go to access that value, there has to be something else that goes and figures out what kind of value it is before we can do anything with it. That's something called the type inference engine. Don't worry about that right now, but because I'm getting a little ahead of ourselves here, but that's kind of where we're going. But it's an extra guy there that before you're allowed to use a value, it has to identify what it is. Okay, so kind of like reaching into a toolbox, somebody pulls out random tool X, and then you have to look and see what it is before you can use it. Okay? As opposed to reaching into a toolbox that you know has one thing in it, and you know it's a hammer before you reach in. You can immediately pull it out and start swinging. That make sense? All right, so difference between loosely typed and strongly typed languages. This is going to segue us directly into starting to talk about variables. And I think we had, remember back at our problem solving slide, human beings use memory, programming languages emulate this through variables. We ask questions, languages emulate this through conditionals. Repetition, languages emulate this through loops. All right, so this will start our discussion on variables, and we'll look at it through the lens of Java first. But while we're introducing this, we're also going to start looking at GameSalad and see how these guys, how a variable in Java is accomplished in GameSalad through something called an attribute. Okay? In here, we will be doing things using GameSalad, but we'll be looking at a traditional general purpose programming language as the example of all the work that GameSalad's doing for us. So Java is a high-level language. We can think of GameSalad as being a super high-level language because it's actually doing a lot of the high language stuff for us without us having to write that code. So it's even a level higher for human beings to work with. Now, before I hit this slide, though, history of programming languages. I'm going to draw a picture on here. I like drawing pictures with this. So, way back when, not necessarily that long ago, we're probably talking 1960s-ish, we had a language that was created called C. C was a high-level, general purpose, strongly typed, compiled, procedural programming language. That would be C in terms of the slides we've looked at. Okay? I'll just leave that over there for a few minutes. Okay, that's what C is. Now, remember, procedural languages, that's the pile of wires we had over here, right? Let's make sure this is still recording. Yep. Okay, so procedural languages are the pile of wires we had over here when we're talking about smartphones versus where we have them as objects versus the pile of wires. So C allowed us to solve a general classification of problem. It was strongly typed, whatever that means for us, so think of it as a fast language. It was compiled, definitely a fast language, but it was procedural. Allowed us to solve complex problems, but showed us a lot of the details. So we can say this was a very powerful language, but had its weaknesses, because human beings solve problems one way, and the goal of a programming language is hopefully allowing us to mimic the way we solve problems. If a human being is building a house, we usually eventually put drywall up after we wire the place, right? Procedural languages didn't let us do that. So we saw C as being a weakness. C was actually originally designed for writing operating systems. So things like Windows and the Mac OS and Linux, things like that. Things that are highly complex anyways. So no matter how hard you work, there's going to be wires shown, right? You go into, I don't know, think about something complex, a nuclear power plant or something like that. Probably going to see pipes and wires and stuff like that. They're not going to put a whole lot of drywall up because it's a complex piece of machinery, right? So C was that kind of language. Well, through C, programmers started trying to manipulate C into allowing us to solve problems in a more object-oriented way. But this is before we had this term, object-oriented, or OOP, object-oriented programming. So in the middle here, C programmers started using things called struts and function pointers to emulate the way object-oriented languages work. It's not that important that you remember this. Okay, I'm just trying to paint the picture. All right, I'll usually point out things that I think are important. I just want to show you where we got to here, so you don't have to remember what a struct is, or, well, I didn't tell you what it is. Don't worry. You'll learn about it in one of the future classes. Okay. So they started doing some stuff to make this procedural language look more object-oriented. That's the punchline there, okay? Finally, somebody said enough's enough. And they came out with the C++ language, which is the object-oriented version of C. Now, the people who adopted C++ was Microsoft. Before that, Apple and Microsoft both used C. Once the object-oriented languages came out, that was after Microsoft and Apple's initial fight, and we'll talk about that here in a second. Microsoft went the C++ route. Well, Apple doesn't agree with Microsoft, so they fund their own project that produces a language called Objective-C. Mac programming, PC programming. Both of these, though, are based on the C programming language. So structurally, they look very, very similar. But they're not equivalent. Okay? Now, from C++, there were some weaknesses with this language. So even though C++ was object-oriented, it allowed programmers to have direct access to memory, which is dangerous for a programmer, especially beginning programmers who tend to make a lot of mistakes. What would happen is you'd be writing your C++ code, you would do something stupid, which you're bound to do when you're just learning the stuff, and you'd have to restart your computer because you'd crash your operating system, because you overwrote part of the memory that your operating system was in. So while C++ was very powerful through somebody who knew what they were doing, it had some caveats for beginning programmers. Beyond that, it also empowered programmers to make bad choices that should never be made. Okay, and to give you a real-world example of this, let's say you're having a party at your house, and you're inviting me to your party. You would probably say, here's my address, show up at 8, right? Well, in C++, you could do that, which makes perfect sense. You can give them the address of something because the house is heavy, right? But C++ also empowered the programmer to decide to allow you to hand me your house. Open the door at 8. Make sense? That would never make sense in real life, correct? Even if you live in a very tiny house. Isn't that like the new thing, the mini homes? I've seen like some reality shows on that or something. Like these guys that like build these like houses that are like the size of a small car but have really cool stuff in them. Something like that. Even those are too heavy for us to just carry around, right? Okay. I mean, even a Maytag box is a little unwieldy. You might tell us where your Maytag box is if you're living in one of those. So, punchline is it would never make sense for you to hand somebody your house. You'd always tell them where they can find it. C++ allowed the programmer to make that choice. Okay? So, a new language was created out of that called Java. And in the early days of Java, many people called this C+++, jokingly, but Java and C++ are extremely similar languages because both languages are based off of the original C programming language. Okay? Now consider this, why these languages are so related. There was nothing wrong with C except it was missing some features. Okay? So they added some new features and rebranded it C++. But you had a whole group of people who already were C programmers. You probably need to make C++ easy to transition to for those people, right? So C++ was built very much like C. If you're a C programmer and you look at C++ code, right off the bat, a lot of it is going to look very familiar to you. Similarly, if you're a C++ programmer and you look at some Java code, right off the bat, it's going to look very familiar to you so that these folks can transition to Java very quickly. Make sense? Otherwise you come up with this goofy new language that nobody's going to use. Okay? Now, Java. Let's throw a slide in here about Java. Java's one claim to fame. Anybody know what Java's claim to fame is? I don't know if you mentioned it in the 150 class or anything. Java was said to be platform independent. Write once, run anywhere. Okay? Now, what this means, and where this didn't exist in C++, if you were a C++ programmer and you wrote a program for a PC, and then you wanted to have that same program for the Mac, you basically had to rewrite the whole program. Because you would write it for the PC, you compile it using a compiler that knew how to translate the high-level program into a low-level source code that the CPU on that PC understood. Well, even at the hardware level, these older computers, Macs and PCs, didn't agree. The earlier Macs used PowerPC processors as opposed to Intel processors. They weren't compatible with each other. Now they both use Intel, but they've come up with new ways to not be compatible with each other. Okay, but in any case, for those of you who are PC gamers, if you were buying a computer, you'd buy a PC because the games definitely come out for that, right? Sometimes you have to wait 6 months for the Mac version of it to be released, if it ever gets released. Okay, Macintosh has become a lot more popular in the last several years, but historically, it wasn't popular at all for gaming, and even today. I mean, what does Windows have? 97% of the desktop desktop market share. So, I mean, Apple's number 2, but we're talking, relatively speaking, a very, very tiny market share. So Microsoft is never going to lose their dominance in desktop. What's going to happen is desktop's going to start going away, moving over towards more mobile stuff. Okay? But in any case, one of the weaknesses with C++ would have been seen as, if you want this program to run on multiple platforms, run on multiple types of computers, you have to write it multiple times. Well, for really complex programs, the first time took a long time. So that's why a lot of software came out for just one platform or the other. So Java was supposed to fix this problem because Java advertised itself as being platform independent. You get to write your program once and it will run anywhere. Okay? And how did Java accomplish this? Let me just throw another little thing in there. Java, if we were to give it the similar treatment that we gave C here. Java is a high-level, object-oriented, general-purpose, strongly typed, compiled language. But I'm going to throw a little caveat in there. / interpreted language. Kind of both. And it was in this kind of both argument that Java was able to accomplish its platform independence. Okay, and let me show you how that worked. So we'd have our Java source. So that's going to be our Java code. We write our Java source code, which is a high-level language. We're going to send it through the Java compiler, javac. Okay? Now remember, compilers convert between a high-level language and a low-level language. That's the job of that tool, right? So now what's created is Java bytecode. This is a low-level language. Okay? And remind me, what's a low-level language? Remember, any of these things can pop up on a quiz at any point in time. 1-to-1. Okay, so every line of code in a low-level language translates into one magic trick that the CPU knows how to do. Okay? So in high-level languages, like our Java source code, every line of code we write is many lines of code, many magic tricks the CPU knows. So we need to get it down to the more granular level. So rather than write it ourselves, we use this tool called a compiler to convert that high-level language into our low-level language, called Java bytecode. Now, in an older language, like C++, we would have our C++ source. We'd run it through our C compiler. This is the GNU C compiler. Actually, the one for C++ is called G++. So that's the GNU C compiler, whatever. These guys are both compilers. And this would produce assembly. Actually, it would produce x86 assembly, which is a low-level language. And that low-level language would run directly on the Intel CPU. Okay? So this is our traditional model that does not support platform independence. For Java, rather than this running on a CPU, this ran inside of something called the Java Virtual Machine, JVM. This is a computer written in software, or a CPU implemented in software. Okay? So this guy up here, the Intel CPU, this is an actual physical chip that's inside of our computers that has all those magic tricks built into it. So this compiler took your C++ code, turned it into a bunch of low-level instructions, which each map to exactly one magic trick the CPU knew how to do. This guy down here took our Java source code, which looks very similar to C++, compiled it, turned it into Java bytecode, another low-level language. We can call these guys synonyms. Okay? But this was a language that translates exactly to the CPU. This is a language that runs through a software-based CPU called the Java Virtual Machine. Isn't it funny when he has on a slide to laugh? How many of you have had Dr. Locklear before? He was on sabbatical last semester, so you usually would have had him for 150. But yeah, it's bad. So the Java virtual machine then flows into an interpreter who interprets during runtime for the Intel CPU. So this interpreter is taking a low-level language and interpreting into another low-level language. Okay? Which then runs on the CPU. So this would be the example of how Java works on a PC. So I'm gonna pretend like they have different CPUs, even though Macs and PCs both run on Intel today. We could take that same Java source code, compile it down to Java bytecode, runs in the virtual machine, goes through an interpreter, and now it's going to run in the Power PC CPU, which is a different type of CPU. PC, Mac, in this example. So the makers of Java, who were Sun Microsystems, now Oracle. Oracle bought Sun Microsystems. What they did is instead of relying on the programmer to rewrite their source code, like we had to do before, when the guy who wrote the video game for PC had to then go and rewrite his C++ code for Mac. Rather than relying on the programmer to rewrite their code, what Sun Microsystems did is they said, you know what? We will port, that's what it's called to rewrite your code. We will port the virtual machine over. So this was the PC virtual machine. This was the Mac virtual machine. So they wrote the virtual machine twice. Sun Microsystems took this upon themselves. They wrote this program twice. And this program knew how to read Java bytecode and interpret it for the Intel CPU on PCs. This version of it knew how to read in Java bytecode, the exact same Java bytecode as this guy up here. So the reality is after you compile your program and you have Java bytecode, you could just take this bytecode to any platform. You don't even have to recompile it to make it work. So it knew how to take this Java bytecode and interpret it for the PowerPC processor. Then we had back then, you would have had the Sun Java virtual machine made by Sun Microsystems, which would have run on the Spark CPU, which is a piece of hardware they made. So 3 different processors, 3 different, dudes who know how to do magic tricks that the same Java bytecode can run on because they each run through a software-based CPU that was written for each of those CPUs, or each of those operating systems by today's example. Because in today's world, Mac and PC would both use Intel processors, but the hooks that are built into the operating systems, the way certain things are accomplished through Windows is different than the way certain things are accomplished through the Mac. So this virtual machine still needs to do things in a different way. Go ahead.
Could you explain how, like, for example, in the example of C++, why couldn't the compiler, if you had different platforms, why would you have to rewrite the source code versus having the compiler be different for each platform?
Generally speaking, if you were just writing console, like the Hello World program, let's say it was a really simple program that just spit the word Hello World out to the screen, you wouldn't have had to rewrite it. Compiler would work on both. But the second you start writing programs that have graphical user interfaces or gaming type stuff, the way Windows are created, and that's why they called it Windows, the operating system, is because it was a windowing environment. You would use their tools, their built-in hooks, to teach Windows, for your program to tell Windows how to create the screen for Microsoft Word, how to create these drop downs over here, all this stuff. Where the way to do that for the Mac would have been completely different, using a whole different library of stuff. To take that to the more modern thing for games, if you've noticed, video games that come out for both Mac and PC, that come out either together or very close to each other, there's kind of two different competing technologies for 3D graphics. One's called OpenGL, which is an open standard that Mac and PC support. The other one's called DirectX, which is a Windows-only thing. Okay, most new graphics cards have both things built into them. Most modern, not just new. Graphics cards have both built into them. If you're writing stuff for Windows, there are some advantages to using DirectX. Microsoft writes the operating system, Microsoft writes DirectX. There's probably some compatibilities there that allow you to pull off some things, some tricks that are more efficient through DirectX. But in that example, if you're going to write a video game using DirectX for your 3D graphics, and you're going to go release it for the Mac, you have to rewrite all that stuff in OpenGL. Okay? As opposed to, if you write it in OpenGL the first time, well, you'll still have to change some stuff because even your game is going to load into a window. There's graphic user interface based stuff that's not OpenGL based on a Mac and a PC game. So you'll have to rewrite portions of it, but at least the thing that makes the stuff spin around on the screen and explosions and all that crap would be the same. But there's certainly some level of porting that would involve. But in our mind, when we think about an application, we're probably thinking about something like this that has a graphical user interface, or something that has, video gamey type graphics or something, as opposed to a command line hello world program. Okay, certainly those would require significantly less rewriting. The only things that would have to be ported over there, just to even give you an example on that, would be like saving things to the file directory and stuff like that. There might be different commands for doing those things, but certainly wouldn't be a complete rewrite. All right, so the idea here is that generally speaking, this was a problem. The fact that even having to rewrite 20% of a really large application was time consuming and probably not worth it. If you were a software writer back then, you were writing for Windows. Even today, if you're writing for desktop computers, you're probably definitely writing for Windows, maybe going to also write it for Mac. Very rarely does a third-party developer not named Apple write their stuff for Apple first. Just kind of makes sense, right? These guys are businesses, they want to make money. Are you going to design your software for these 10 people or for these 10 million people? It just kind of makes sense. But developers would like to write it for those 10 million people and also get money out of those 10, if it was no extra work on their part, correct? So that's where this idea of platform independence came in. All right, so Sun Microsystems decided we're going to port the Java virtual machine multiple times so that the programmer doesn't have to write their software multiple times. But this still requires now an interpreter, which will slow things down. Like I said before, computers are really, really, really fast. So how much this slows it down might not be noticeable for many applications. But for video games, it's enough of a slowdown that it's probably not worth it. Okay? Now, having said that, Microsoft, being who Microsoft is, decided to steal Java. So they came out with a product called J++. This was Java syntax that ran in Microsoft's, that was codable inside of Microsoft's development tool called Visual Studio. Not all that important, but this was Microsoft's language. Okay? Microsoft has a very interesting business model. Microsoft typically steals stuff, gets sued, and settles outside of court. And there's nothing wrong with that. Our legal system allows for it. Okay, from a business perspective, when everything's about timing, if you're a large company that has a lot of cash, Are you better off spending 8 months developing something or spending 15 minutes stealing it and then paying the price in court? Even if you're going to go and buy the company, you might spend 6 or 7 months negotiating the deal. So you're better off as Microsoft to steal it and pay the price. You know, if you're, some 18-year-old who wrote some really cool software in your grandma's basement and Microsoft steals your stuff and you get all pissed off and then you sue them and Microsoft says, oh, we're sorry. How about we give you $10 million and you go away? Well, you maybe put your pants on because you were probably in your underwear. Okay, and you cash the $10 million check, right? That's how Microsoft does business. No biggie. Okay, you probably wish you were the 18-year-old who got the $10 million check from Microsoft. Who cares if it could have been $20 billion later on? You come up with that idea then. Right now, I can spend a while blowing through $10 million. So Microsoft decided to steal Java from Sun. Problem is his son wasn't the 18-year-old in his underwear programming out of his grandma's basement. Sun is a multi-billion-dollar company in its own right. And they weren't going to get paid off quite so easily. They took Microsoft to court, and they won. Microsoft had to pay them a lot of cash, and Microsoft had to stop making J++. Okay, no longer allowed. Now, in that interim there, Microsoft also wrote their own version of the Java virtual machine that in some ways allowed certain things to happen more quickly because they knew about how Windows completely works, where Sun was having to work with the public interfaces that Windows allowed third-party developers to use. So for some applications, Microsoft's version of the Java virtual machine for Windows was actually higher performance than Sun's. Okay, but this had to go away as well as part of that lawsuit. Now, so Microsoft got sued, lost, paid a lot of money, and was forced to write the software on their own. So this led them down a path to create a programming language that they called C#. Okay, so I'm going to start there next class. Okay, now first of all, I'll say based on some of the feedback I'm getting from my questions I'm asking you here, I would say it's highly likely I'll give you a quiz on Monday. So make sure you're reviewing things like if I asked you what's a compiler, be able to tell me what that is. What's the difference between a high-level and a low-level language? Be able to tell me what that is. All right, I will see everybody on Monday.